Okay, hello everyone. So the first talk of the afternoon is by Yasaman Bahri on computation in wide networks.
Thank you. First off, I wanted to thank the organizers for giving me the opportunity to give this talk here. And also thank my collaborators. I'll be talking mostly about papers 1, 3, and 4, which was primarily done with a bunch of great folks at Google Brain, namely Jae-Hoon Lee, Roman Novak, Jeffrey Pennington, Sam Schoenholz, Joshua Zoldikshi, and Lichao Xiao. And also special thanks to Greg Yang at MSR and Jerry Huron at Cambridge. So I guess to start off and maybe give some little bit of philosophy, I think we would all agree that we're kind of in this early stage of trying to better understand deep learning and what one typically might do in some field of science, theoretical science, and trying to understand understand some complicated system is to try to tease out, at least empirically, phenomena which are semi-universal, which one would want to understand and are not too microscopic a question. And then theoretically, when you don't have a place to start, you typically might take limits of a problem in certain variables which you think might be important. And then try to, once you identify that limit and try to solve it, maybe try to study corrections about that or do some sort of perturbative analysis. And so that was where we began thinking about deep neural networks. We started with thinking about networks that are very wide, so infinitely wide, but let's say the width is larger than any other relevant parameter in the problem, and fixed depth. And I apologize that this talk is mostly a survey of our older work, but hopefully I'll try to point out maybe some interesting things that you could walk away with. And the 3 points that I'll try to get through is that we want to try to characterize randomly initialized neural networks, specifically the distribution over functions that are computed by such networks that are infinitely wide. What happens when you train such networks in a Bayesian setting, focusing on 2 specific cases of fully connected and convolutional neural networks. We'll then do some empirical comparisons to neural networks that are trained with, that are finite width and trained with some sort of stochastic optimization. And then finally, I'll get to stuff that is more recent, so describing networks, again, in this infinite width limit after gradient descent optimization, which is essentially the neural tangent kernel line of results, but focusing on what happens in parameter space, and maybe make some pointers. So a bunch of previous talks have kind of alluded to this, what happens to the generalization gap as you make networks wider. And certainly some earlier papers had pointed this out. I personally saw this in a paper by Benham Neshapur a while back now. And we repeated such experiments for different kinds of architectures. So on the left, you see an experiment that looks at the generalization gap across a variety of models, all within one fixed family, fully connected networks, as you make them wider. And on the right, you have the same thing, but now it's plotting test accuracy. All of these models have 100% train accuracy, but you see that as you make either the size of the hidden layer in the fully connected case or the number of channels in each hidden layer larger, that you see an improvement in the accuracy. And so it's natural to wonder what happens in the limit of infinite width, and this is kind of what motivated us to start studying this. I will try to point out, though, that I think these plots probably require a little bit more subtlety in how they're made, and by the end of the talk, you'll kind of see that if you believe in the infinite width result, that there is some discrepancy between finite width and infinite width performance, and perhaps that really means that if one were to make such curves or study such curves a little bit more in a nuanced way, maybe for particular families of models, choosing hyperparameters in a certain way, that you would actually see that it would bend down at certain point, suggesting that there's actually a performance difference between infinite width and finite width networks. But that's kind of where we're working towards. And also our starting point, this was a while back now, which is obvious in retrospect, is that it's useful to think about the functions that are realized by neural networks and not just take a parametric point of view, which I think from my perspective, had been kind of the subject of discussion that I had seen. And these could be end-to-end functions realized by the network or functions realized by intermediate layers. But it's interesting to study the functions, particularly in neural networks where the parameters lack a clear meaning and they weren't really designed to be interpretable. There's a high amount of redundancy in their description. And in particular, the first question we're going to answer is like, which classes of functions are we biased towards as a result of initialization? And there's going to be a very simple answer to that, which I think is interesting to think about in light of like function complexity. So in terms of count of number of parameters, it seems that even at initialization, you have a function that's very complex, but in terms of the class of functions that you're realizing, you're moving towards something that's rather simple. And in general, I think it's interesting to kind of move between thinking about distributions over neural network parameters and distributions over functions, whether that's at initialization or during the course of some kind of training. So where we started with this, again, now a while back, was inspired by a paper from Radford Neal from the mid-90s, where he had made a connection between single hidden layer neural networks that were infinitely wide and Gaussian processes. And the connection is basically about the distribution over functions that are realized by such networks. So specifically, let's say you have a neural network which just has a single hidden layer, has fully connected topology for right now, and you have an IID prior over parameters. And you also need to scale these parameters, the prior over parameters, in a specific way so that everything is well defined. So just as we do when we usually initialize neural networks, you need to take the variance of these parameters to scale as like 1 over n or 1 over the width, so that the variance of the output that you get as you take n to infinity is order 1. But let's say you have that setup, and this is the computation that the neural network does. And I'll use this to kind of also introduce notation that I'm going to try to stick to through the talk. So z, the variable z, is the pre-activation after application of one hidden layer. I is the index for a hidden node. X is the input. And weights and biases are W's and B's. And I keep sometimes the dependence on the input to specify that we're looking at these functions z of x. So this is the computation that is done. And then Neal pointed out that as you take n to be infinite, that the distribution on the output converges to a Gaussian process. And this follows from the central limit theorem, because you're summing over infinitely many variables. So specifically, to be concrete, let's say you take your your output weights to be normal with mean 0 and variance, which is again scaled properly, and biases that are mean 0. And I'll stick to mean 0 priors for all the parameters throughout this talk. So all the GPs, Gaussian processes, will be mean 0. Then you want to compute the characterization of the GP. So mean here is easy, and everything is in this covariance function k, where superscript 1 means is the layer index. And if you imagine plugging in this expression here, you're going to get a contribution from the bias variance, contribution from the weight variance, and some function of x and x prime.
So, just a question. So there is no attention here to inputs and training, just a generative model by randomly picking weights?
Yeah. It's the prior over, so it's some neural network with some prior over parameters, and what is the prior over functions that you realized for right now. But then you'll see you can say something about the trained networks in a bit. So that was what Neal did in the 90s, and then we asked kind of the same question about deep networks. So again, the same setup. The network has fixed depth, fully connected topology, IID prior over parameters with the parameter variance is scaled properly. Then the claim is that the distribution on the output is also a Gaussian process as you take the width to be infinite. In our original paper, we didn't have a rigorous proof of this. We just argued it from a sequential kind of perspective. So like by induction, we know that Z1 is governed by a Gaussian process after you take the first hidden layer to be of infinite width. And then you kind of repeat that. And if you, that's kind of maybe like a very hand-wavy way to argue it. But then the claim was that Z was governed by some Gaussian process with some kernel K or covariance function K that we need to compute. So that was in our original paper, and there was a paper that appeared simultaneously also by Alex Matthews, published in ICLR, that proved the same statement rigorously. And you don't need this sequential limit of taking, you can also prove it when the minimum of the layer width also goes to infinity. So it's been proven more rigorously since then, both by Matthews and a later paper of ours. But so given that, the thing that you want to now characterize is the mean and covariance function. And so this covariance function, denoted k to the L as a function of input x and x prime, is just this expectation. Imagine plugging this in. You get a contribution from the bias variance, contribution from the weight variance, and then you just need to compute this expectation of these two phis of the pre-activation signal that's coming in for these two different inputs, x and x prime. Given that the z to the L minus 1, the signal that's coming in, is governed by some Gaussian process with covariance function, which you know. So this looks like a lot of notation, but it's just a 2D Gaussian integral. So we can kind of characterize the result just in this one boxed equation, which is that k to the L as a function of x and x prime is some function c sub phi, which only depends on the choice of nonlinearity. And it also depends on what comes in, the covariance function k to the L minus 1. And you also have this base case before you apply any nonlinearity, which just amounts to computing inner products between the inputs x and x prime. So we summarize this description of the neural network that's infinitely wide at initialization by saying that z sub L is governed by this GP, mean zero, covariance function k to the L, and symbolically this is the recursion relationship that's satisfied. So again, still working at initialization. You can ask about properties of this GP. Sometimes I'll refer to it as the NNGP to say it's the Gaussian process that corresponds to this neural network. So these these recursion relationships have appeared in the literature before in another setting, not connected to Gaussian processes. So Cho and Saul, for instance, have earlier work where they essentially define these compositional kernels or defined it in this way and then calculated it for ReLU. So it turns out you can get closed form expressions for ReLU for this sort of thing and also for certain other activation functions. And you might ask, for instance, what is the structure of this covariance function? And this is one plot that kind of shows it. So this is plotting, it's a 1D plot of x and x prime that are two vectors where x prime is rotated by angle theta from x. And so you know, before you apply any nonlinearity, you just have a dot product. So x dot x prime looks like a cosine. And then as you iterate that through a certain number of layers, that covariance structure gets bent in a certain way. And that's the flattening that you see here with depth. So that flattening or loss of structure is something that you'll see comes again as you iterate the recursion relationship. And so now to return to the earlier question, given that you map the problem onto a Gaussian process prior, it's kind of a textbook result to then do Bayesian inference with such a prior, especially if you're just going to do it with squared loss. And the nice thing about Gaussian processes is that if you do Bayesian inference, you can just ignore parameter space altogether and do it all in function space. So these integrals that are in principle over these infinite dimensional vectors are reduced to just integrals over these function values. And for squared loss, all of the entire integrand is just one Gaussian, so you can do them exactly. And excuse me, the result you get is that the distribution on the output Z star, given data set D and test point X star, is given by a normal distribution with mean mu bar and variance k bar. Excuse me. And so this just reduces the problem of doing Bayesian inference to doing linear algebra. You just have to compute these covariance matrices on the data set, which is size n by n. You have to invert them and take various inner products with the target vector and this other portion of the covariance function of the test point against a data set. And so you've just removed all of the optimization or integration that you're going to do. You're just going to do linear algebra. So in our original work, one of the things we were curious about was if you empirically compared the result of implementing Bayesian inference using this neural network Gaussian process, how would that compare to the result you would get from training a deep network at finite width with some variant of gradient descent? And because we wanted to do an apples-to-apples comparison between the two, so we were using, thanks so much. Because we wanted to do an apples-to-apples comparison between Bayesian inference with a squared loss, we also trained on MSC when we were doing gradient descent. So these are the results I'm going to show here are not cross-entropy neural networks where we know the networks do especially well. But the neural networks that are trained with gradient descent are all hyperparameter optimized. We tried different nonlinearities, different learning rates, different kinds of optimizers, all within the fully connected topology. And for the kernel computation, we either computed it in closed form, where we had where that was available for particular nonlinearity, or we used numerical interpolation for that 2D integral that I showed earlier for nonlinearities where we didn't have an expression. And we implemented Bayesian inference, which requires that matrix inversion in the data set size, which is quite costly in the data set size. We do that exactly. And so these were the results we got back when we did them. They're not very great test performances, but at least you see that along each row, there's a comparison between the type of test set and the size of the training set. And then there are 4 comparisons, neural networks and GPs. And when you, what's the best of the 4 in a row is highlighted in bold. And you can see at least that although the performances are not great, that typically the GP does as well as or better than the neural network trained with MSC loss. And in general, the widest neural networks were the ones that were doing the best as well. And this goes up to the full data set size, which for CFAR, where you get this result. As an aside, we also studied the performance of these of the NNGP, so using Bayesian inference, using just linear algebra, as a function of depth for different nonlinearities. So the top row shows tanh as the depth of the network, or the depth of this recursion relationship that you iterate to is increased. And the bottom is for ReLU. And the best performing networks are the ones in purple. And what you see is that as you iterate with depth, that the best performing networks are concentrating along particular lines or curves. And that has to do with what I alluded to earlier, where you saw that with depth, you were starting to lose the structure of the covariance function. Because you're not connected to the input signal anymore, you're just iterating the same thing over and over. And it turns out that these sorts of recursion relationships, at least asymptotically with depth, had also been studied before in a different context, where the idea was that maybe looking at fixed points of that recursion relationship was a proxy for good trainability for networks. So you can imagine that it's some estimate where if I'm losing the structure of the covariance function, meaning I'm losing the structure between 2 different inputs, x and x prime, then maybe I don't have enough information to train. And those are regions of hyperparameter space, in this case just a 2-dimensional space of the weight and bias variance that I should try to avoid. And so previous work, kind of known under the name of mean field theory, starting with these 2 papers, had studied these recursion relationships with depth and identified different fixed points, and also kind of studied the length scales over which you start to approach this fixed point. And the idea is that you don't want your network to be much deeper than that length scale, because that's kind of the characteristic scale over which you've lost the signal between the inputs and might not be able to train. And so that those curves kind of line up with those fixed points computed earlier, precisely because we're kind of thinking about the same quantity and iterating the same recursion relationship with them. And then finally, another experiment or comparison we had done was to look at the comparison of this NNGP against, again, these finite width neural networks as a function of increasing width and training data set size. And again, now you see it summarized here in a slightly different way, that the NNGP tended to do as well as or better than the best performing neural networks, which were typically the widest, which are the ones shown in blue. And so to conclude this part, kind of what we walked away with from this original paper was a compact description of deep fully connected networks in the infinite width limit, both at the level of the prior. So now it's kind of easy to see that you're biased towards a very simple class of functions. And then you also have in hand, at least for squared loss, like an explicit Bayesian posterior for this limit. And then numerically, we had seen that it seems that with SGD, in the fully connected topology, that you were performing about as well as the NNGP.
Yeah, now something, so it is explicit formalized only for regression, right? So if you do something else like classification, and then you have a very big model, doesn't that kill you then? Because you have to do the MCMC then.
That's right. And because we didn't really have expertise in that, we didn't do the case of like cross entropy. It was about loss, the choice of loss, like cross entropy versus squared loss. So that's why we didn't do that sort of thing.
Classification, right?
Yeah. So we only did really regression, and like classification performance here is kind of just choosing a max over the like. So it's regression to the one hot targets is kind of what we did. Because we didn't know how to do, we didn't really have expertise in that also, and we were worried about like what approximation or how not being able to do the Bayesian part exactly, and then what the trade-off would be with gradient descent. But I expect there that like, well, cross entropy is a good loss, and that's where you might see the largest. I'll come back to this maybe towards the end, but you might see the largest deviations from the infinite width limit. But at least for this topology, it seemed like it didn't, and squared loss, it seemed like there wasn't such a big difference. So that was the case for fully connected. We then moved on to convolutional networks. So again, you just take the channel dimension to be infinite. And in this first paper, which I won't really go into, we studied the signal propagation mean field theory, so like what happens asymptotically with depth. But I'll focus mostly on this paper, which is where we do kind of flesh out this conv GP neural network correspondence and then repeat the same set of experiments comparing conv GPs with finite width convolutional neural networks that are trained with some kind of stochastic optimization.
So you saw comparison between neural nets and the GP. Is it correct to view this as just a comparison between the maximum likelihood as opposed to the Bayesian posterior? Because, I mean, in particular, are you using L2 regularization? The L2 regularization, if I understood everything correctly, maybe this is sanity check what I did, L2 regularization on the weights would correspond to the likelihood under your prior. And so, sorry, not maximum likelihood, but map. So training the network with regularization would give you the map estimate. And so, of the GP. So is essentially what we're seeing here, the difference in the map estimate and the actual expectation, or is?
I guess that could be one way of viewing it, but maybe another way of viewing it is also, so we did have regularization as a hyperparameter in there, I believe, but sometimes it could be 0. But I would say, but a different perspective is that like what's happening with gradient descent is really NTK, at least like as you make it wider. So maybe it's also a comparison between those two.
Okay, we can.
But I'm not positive that I.
I use the active regularization and you trust your optimization. then you should just get the map as a mesh, unless I'm missing something, is the map as a mesh for your GP.
If, with gradient descent, you're saying you're...
And you trust your optimization, right? I mean, so there's any way there's an issue of optimizing. And also for the GP, you have numerical issues of how you calculate that. And if I understand everything correctly, if you trust your optimization, then training the network, because if I understand correctly, this corresponds to finding the map estimates for the GP. Is that correct, or is...
that's not, we don't,
I guess the question
yeah.
Is the difference in map and Bayesian and the computation the mean posterior and posterior mean, or is it because of difference in optimization methods?
That's a good question. So I don't feel confident in answering that. Maybe we can chat about it later. Yeah, so we repeated basically that same set of experiments for the convolutional case. And so I was going to walk through that. And so just to work through what the covariance function looks like for the conv case, so, and also introduce a little bit more notation. So now the pre-activations after layer L have this channel index I, but they also have a spatial index alpha as a function of x, and they depend on the input x. Right now we're just going to do 1D spatial indices just for simplicity. But we have to keep track of both I and alpha. And this is kind of the computation you have with a conv filter. So here, omega to the L, ij are output-input channel indices. Beta is a relative spatial index. And so the Greek letters here are all tracking what's happening spatially. And so similar setup, let's say your parameters are drawn IID, where you have the weight variance of the filters, again, scaling with 1 over the channel size, and I apologize, I went from little n to big N here. But then the claim again, and we have a more rigorous proof in this paper this time, is that as the number of channels increases, the distribution over output functions is governed by some GP, and now we just need to compute the covariance function. And so the covariance function now is this object k to the L alpha alpha prime, which depends on 2 inputs x and x prime, so different spatial indices. And imagine plugging in this expression here. You get a contribution from the bias variance, and then this expectation here, where you do a little bit of spatial averaging over beta. So that's kind of the effect that weight tying has. You're kind of blurring along alpha alpha prime. And to summarize that, let's just write it as some function c, which also has spatial indices here. And it just is shorthand for doing this second moment calculation, given that what's coming into that layer is also a Gaussian process with some k, covariance k to the L minus 1. So this is just for pure covariances, pure convolutions after a certain number of layers. With CNNs, you have a lot more architectural design choices, which makes it more complicated. But let's do 2 main ones that I'll focus on, 2 kinds of choices of end aggregation into 10 output classes, which will give us 2 different kinds of Gaussian processes. So the first one is where we do the following. So we take the output, here it's this z to the L of x, and we have both a channel index and a spatial index. We flatten it over both indices together, and then we just apply we pass it through a nonlinearity, and then we apply a dense layer. This is the W final ij. And this sum is over the product of those flattened indices, which is channel and spatial dimension. And so this is, again, some GP, but now the covariance function, if you were to calculate it, basically requires that both the channel and the spatial indices match. So then what you get is just a sum over the diagonal pixel elements, alpha alpha, rather than different pixels mixing, like alpha alpha prime, which would be a more general thing. So in this particular case, when you terminate in this way, you lose the covariance between different spatial locations. And also an observation from the previous slide is that the spatial diagonal continues to map to the spatial diagonal, so that's all you need to keep. That means that the computation of this covariance matrix will be computationally easier because you have fewer indices to keep around. But what you lost in this limit is also the effect of weight tying. So you could have gotten the same result if you had just considered locally connected networks up to that layer. Locally connected meaning you have filters that still have some small size to them. So they're spatially restricted, but they're not weight tied across different spatial locations. So if you had just done that and then terminated in this way, you would have gotten the same covariance function. So you've kind of lost the effect of weight tying with this kind of termination. And then the other termination that we consider is one, like in its most general form, is one where you take the signal and you project it onto some vector spatially. So now alpha you project it with some vector h alpha and sum over alpha. And the case that I really just want to focus on is the case of global average pooling, where you just sum over all of alpha together first. That's what you do. Let's say you sum over the alpha index here over the entire image, and then you just need to apply a dense layer to the channel index. And if you do that, the covariance function you end up with is written down here. So you end up mixing different spatial locations because you did this average pooling before you did this application of a dense layer. And so you have this sum over alpha, alpha prime, which, as you can kind of maybe guess, gives you a richer covariance function because you've had some you've kept some covariances between different spatial locations. So this is one kind of empirical comparison between the various NNGPs. And I won't discuss all of them, but maybe just highlight a couple. So one is the fully connected case, which we talked about before. This is also for a small training data set size, which is why the accuracies are so low. So as a function of depth, that's the brown line here, the fully connected case. The green one is the case I described where you just have pure convolutions and you have a dense layer where you flattened everything. So you see that there's a little bit of a gap between fully connected and that case. But then there's an even larger gap to the yellow line, which is the case where you do convolutional pure convolutions and just do global average pooling at the end. So that better covariance function. And you do see a gap in performance between those two. Just as an aside, like for some of these things, we don't have access. We didn't really track the exact covariance function. So there's a version where you could write down the exact recursion relationship and compute what you get. And then sometimes to have access to make it computationally easier, or to have access to a different class of architectures, we sample the covariance functions and average over different instantiations of the random networks. So that's just an aside as to what the MC means here. And that introduces some kind of approximation, which I won't really discuss probably, and we haven't really studied in a lot of depth. But at least even from a purely architectural viewpoint, you see that there's a gap between the average pooling and the case where you just flatten and apply a dense.
And for reference, just what's the performance of the actual CNN trained with the 2000 example?
That's a good question. I don't have it for this, I think, but I have it for, I'll show a table at the very end which has all the comparisons, and that will be better. And you'll see that in a minute. And so there are so another way to view some of the data is that if you looked at certain initializations and then looked at what happens as you increase the number of channels, so this is part of your question, but again, for small data set sizes, the red lines are the GP and the blue lines are the finite width neural networks as you make them wider. And in certain cases, like depending on how you choose these initializations, sometimes you observe this. But then when you kind of aggregate over all of the hyperparameters that you have, including learning rate, different activation functions, and such, you find that there is a gap between the finite width neural CNNs and the GPs. And that's kind of summarized in this table. I want to maybe point out, walk through some of the rows. So the bottom row is the case of the fully connected networks, which we talked about earlier, and we repeated some of those experiments. And again, we saw that the GP was actually a little bit better in this case. So this is test error now. I apologize, rather than accuracy. But this was FCN is just a regular neural network over hyperparameter optimized over width, depth, learning rate, and batch size, etc. But all for MSE. And that's the FCN GP. This row here is the CNN GP just with a dense layer, so with no pooling. And I won't, maybe I'll come back to what's in parentheses, but if you just look at the numbers that are not in parentheses, CNNs with small learning rates or with certain activation functions like ERF kind of fall in the same ballpark as the CNN GP, but then CNN with ReLU and large learning rate does have a noticeable gap from the CNN GP. And note that that gap could come from a variety of places. It could come from finite width. It could come from ReLU and large learning rate effects with gradient descent. It could also come from the fact that maybe the termination that you did in this infinite width limit was not a good one. And so here we already see this gap, even though this is just a gap for MSE loss already between the some kernel limit, which is not quite the right kernel limit, because this predates, this paper predates us knowing about NTK and that line of work. It was done a little bit earlier, but you see some gap. And then the best case is like a CNN, this is finite with CNN with average pooling. And that was an experiment that for the GP case, we could never scale up to do the full data set size to make that comparison. So we guessed that there, too, there would be quite a bit of a performance gap. This is maybe to be contrasted or compared with a recent paper by a group at Princeton and I think maybe CMU, where they do NTK for the conv case implemented exactly. And there they get better performing kernels, but that's because they're looking at the case of pooling where we know it's better. And that was an experiment that we were never able to implement. We just, on the full data set size at least, we implemented the dense case. But there they also see some gap that's of order 5 or 10% between finite width networks and the infinite width result.
There's a question.
So maybe you have mentioned this. What's the intuition about different pooling? Why different poolings could have different effects?
We haven't studied it in too much depth apart from that, having more information across different spatial locations is good. We haven't kind of dug in deeper to see how it's reflected, say, in the spectrum and things like that. And we haven't considered more complicated cases where you put in pooling in earlier layers and also see what effect that has. So this was just two cases we tried.
So what are 2 cases, I guess?
2 cases are, one is where you have pure conv, but you just flatten over channel and spatial index, and then you apply a dense layer. And then your covariance function there loses the alpha prime. And then the other is where you do global average pooling at the very end. Combat on time, so it's 5. So maybe a summary of this part. So for the fully connected topology, we didn't see much of a gap, even for MSE loss. For conv, we did. And then given that Bayesian inference in this limit was simple to describe, we started to wonder if we could say something about the distribution under gradient descent also in this limit. And that was kind of the question we walked away with after the fully connected. We worked on the fully connected NNGP. And in the interim, other people actually solved this question, open question. So can you say something about the behavior of gradient descent or gradient flow in the infinite width limit? And the result, I hope I didn't miss any references, but Jason talked about it this morning very nicely, was that you evolve according to some frozen kernel, which is the NTK kernel. And this slide is now a little bit kind of redundant in light of Jason's talk in the morning. Maybe the one takeaway is that when you think about this parameter to function space kind of transformation, this quantity theta t, which is the generalization of NTK kernel, it's just this defined to be the derivative of the function map with respect to the parameters contracted over all parameters. It's, in general, some dynamical variable. And to think of this as kind of a special dynamical variable that governs what's happening in the network is, I think, one interesting takeaway that's useful even outside of the NTK limit. So thinking of this theta t as some dynamical variable that's governing the evolution. And I will skip kind of reviewing what these results actually are about. So just if you calculate like the gradient, the rate of change of the parameters and the rate of change of pre-activations at internal layers for a specific hidden node, you see that they vanish in the width going to infinity limit. And so the kernel, as a result of that, is frozen. I will point out that like this NTK kernel is that the NNGP kernel plays a role in the NTK recursion relationship, as you would expect, just because the NNGP kernel is coming from essentially gradients with respect to the last layer weights. It's just this covariance of the final features, features in the final layer. So that's theta L is k to the L, which is the NNGP, plus some other stuff, which also includes the NNGP in it, because you continue to use that every time you calculate these expectation values. You assume that the pre-activations are drawn according to an NNGP kernel. And you start with this base case where theta naught equals k naught. So this I'll also mostly skip. So we had been working on some work trying to understand what dynamics occurs in parameter space, given that this dynamics occurs, the NTK dynamics occurs in function space, without maybe fully knowing the extent of results that were already out there. And so, as Jason mentioned in the morning, NTK is consistent with a linearization of the model about the initial set of parameters. So just doing a first-order Taylor expansion and plugging that in as a substitute for the network, and that becomes an exact thing to do as width goes to infinity. And something that was also pointed out in other papers, including the ones that I referenced previously. But one of the things you can get out of that, with that are, for instance, that the predictive distribution over the model output Z star given some test point X star and data set D is this normal distribution with a mean and variance that, again, involves the NTK and it also involves the NNGP kernel K. And this changes with time as you run gradient flow. And we also had some empirical comparisons between, for instance, if you looked at the mean prediction over an ensemble of, say, 100 networks for, say, like a linear 1D linear interpolation between 2 points, which are the 2 points shown in black, you tend to see that, well, there's a variance prediction coming from this result, there's a variance prediction coming from an NGP, and then there's one that you can calculate on this finite size ensemble, and you see that that variance is well described by NTK in terms of the fluctuations of the prediction along this one-dimensional line, for instance. And I'll refer you to the paper for more experiments. So we basically did a bunch of comparisons, still not state-of-the-art models or anywhere close to that, but between wide neural networks with no approximations and their linearized versions. So maybe one footnote to that is that these are comparisons between not the exact kernel of infinite width, but just the first-order Taylor approximation, which is itself like a random features method with a finite number of random features. So that itself has some approximation. In general, like when the data size is small, when the learning rate is small, when the network is wide enough, there's better agreement. This is maybe the best one we had in that paper, where it's a network that has MSE loss. It's ResNet-like in that it has like batch norm, ReLU, and conv in it, but it's all everything is wide. So there are no restrictions on the channels. They're all like of order 1,000, and it's a comparison between the neural network trained with MSE loss on the full CFAR10 data set against its linearization. And you can see that, so that's a comparison between the solid line and the dashed line. And you can see that basically at late times you start to see the deviation, but at least up to a certain accuracy, there's an agreement between the two. And this was like the largest data set size that we had. push these experiments up to. So maybe just to close, part of basically what I talked about was trying to have a full characterization of what happens to neural networks at infinite width, whether you take a Bayesian approach or train with gradient descent. We have descriptions both in parameter space and function space. I talked about, at least with squared loss, like a description in function space. I didn't say anything, and nobody's kind of really put work out there yet on what happens in parameter space in that same limit. But maybe we're pretty close to kind of completing this table at infinite width. So I will say maybe then in closing that although I think probably state-of-the-art architectures which have restrictions on the number of channels that they use will be far from being described by NTK dynamics. There are networks that are very commonly used, maybe not for actual performance reasons, but certainly things that we use in papers to do theory comparisons for. For instance, fully connected networks, maybe with MSE loss, which might be kind of have the performance of something you could get with a kernel. So that's maybe one takeaway from this. And then I think also that even if like dynamics is not well described by the finite width neural network and the kernel, there are pieces of that that could still have impact on other things. So for instance, just like signal propagation or trainability, a lot of that might be inferable from studying the NTK kernel. And then also, like, are there kernels with impressive test performance? I don't think we've really searched the space of these kinds of compositional kernels anywhere nearly as thoroughly as we have searched the space of neural networks. And current work in progress, which I'm happy to chat about offline, is trying to identify and understand the gaps between NTK and deep neural networks. And I'll close there.
Questions?
So there are also these deep Gaussian processes which are somehow related, but not exactly the same thing. So how does that relate to your work?
So I'm not super familiar with this, but my understanding is that in those models, they usually put a restriction on, you could think of it as a neural network, which has restrictions on the width in particular layers, and they do that precisely so it doesn't collapse to a single GP. They say that it's kind of like a true composition of GPs. I think it's maybe interesting to think about that as a prior closer to like networks that maybe have a restriction or something. But they're different in that all of these were like networks that have all the layers pretty wide with no bottlenecks in the size of the layers.
So I just want to comment on this central limit theorem. So if you do this high dimensionality space, then what you're doing is you are Gaussianizing the PDF or marginal, but the non-Gaussian information is still there. It just has been sent into correlations between these variables, which are much harder to extract. So in other words, the non-Gaussianity in the information theory sense hasn't changed.
And that's an interesting comment. I mean, do you think that maybe those are important then? They especially at finite width, they stay, and maybe they're important in how
Yeah, I think they're important.